In this screencast, we're going to take a look at how unstable atoms behave. Some vocabulary that you need to be aware of is spontaneous, which means it happens by itself and releases energy. Isotope, which is a review. It's an atom of the same element with a different number of neutrons. And frequency, which is the rate per second of vibration of a wave. Radio waves vibrate at certain frequencies, and that becomes important when we start talking about radioactive decay. Radioactivity is the spontaneous release of particles or energy from an atom that is caused by the atom's instability. It was discovered and named by Marie Curie, who won the Nobel Prize in Physics in 1903. The universal symbol for a radioactive substance is shown here. So why then are some atoms unstable? Well, in all atoms, the positively charged protons in the nucleus repel each other due to magnetic repulsion. And in big atoms with a lot of protons in the nucleus, this repulsion can cause instability. If the forces that are holding the nucleus together, so if the strong nuclear force isn't strong enough to hold it all together, the nucleus will more than likely break apart. An example of that is what we see here with polonium-210, which has 84 protons and 126 neutrons in the nucleus. The nuclear force is not strong enough to hold all of those similarly charged particles of protons inside the nucleus, and so the nucleus breaks apart and we have a radioactive decay. Certain elements on the periodic table are radioactive. All isotopes of technetium, which is atomic number 43, and promethium, atomic number 61, as well as all elements with an atomic number greater than 83, which is bismuth, those elements are all radioactive and they are called radioisotopes. Many other elements have at least one radioisotope, and this includes carbon and sodium and iodine. There are several types of radioactive decay. The radioactive decay in which the atom changes from one type of an element to another is called transmutation. So we have alpha decay, beta decay, positron emission, electron capture, and gamma emission as the types of radioactive decay. Alpha decay is symbolized by the Greek letter alpha, which we see here. The unstable nucleus of the radioisotope will emit a helium nucleus, which is going to have 2 protons and 2 neutrons. The alpha particle is relatively large and is slow, and it can be shielded by a piece of paper. So in this graphic, you can see the penetrating power of the type of radiation, and alpha decay is not very strong. An example of an alpha decay problem would be when we take polonium-218, and we remove that helium particle from the nucleus, we end up with lead-214. So how do I do a nuclear decay equation? Well, I need my atomic masses and my atomic numbers to be the same on both sides of the yield sign. So here on the left, I have a mass of 218 for polonium. On the right, if I know that I'm losing a helium atom, which has a mass of 4, what's left for my atomic mass will be 214. On the left, if I start with an atomic number of 84, and I know my helium atom has an atomic number of 2 because there are 2 protons, then what's left to balance that out is 82. And when I look up atomic number 82 on the periodic table, I see that it goes with the element lead. So that's how I know that the decay equation works out that way. The parent isotope is going to split out a helium nucleus and become a daughter isotope. So the parent isotope is what we start with, and the daughter isotope is what we end with. So in other words, polonium-218 loses 2 protons and becomes a lead nucleus. It also loses 2 neutrons, so its mass is going to be decreased by 4. Beta decay is symbolized with the Greek letter beta. And here we see in beta decay, a neutron will become a proton and a fast electron gets emitted. So that's what we're seeing here. Beta decay can be symbolized by this beta symbol, or you can replace this with the letter E. Sometimes it's written like that. Okay, so it would be E with a 0 and a -1. So either way is fine. Okay, so in this example, we have lead-214, and then an electron is emitted, okay? And so we're left with the same mass, 214, but our atomic number is going to increase because 83 minus 1 gives us 82. The element with an atomic number of 83 is bismuth. You can see that beta decay is a stronger radiation than alpha decay because it can go through the paper, but it will be stopped by a piece of aluminum foil. Next is positron emission, and a lot of times this is symbolized also with beta, the Greek letter beta, but a lot of times it has a plus sign at the top. So beta plus as opposed to beta decay, which would be beta minus. Okay, so what happens here is that the proton becomes a neutron, which stays in the nucleus, and a positron is ejected from the atom, and we see that happening here in this diagram. Okay, because this is beta decay, it's also going to be shielded by aluminum. And so what we see here is an example of a reaction is we start with boron. Boron has an atomic number of 5 and it has a mass of 8. As we eject this positron from the nucleus, it has no mass, so our atomic mass stays the same, but it has a positive 1 charge. So I have to subtract 1 from my atomic number to get 4, because 4 plus 1 will give me 5. The element that has an atomic number of 4 is beryllium, and that's how I solve my equation. Electron capture is the opposite of beta emission. So the capture of the electron lets a proton turn into a neutron. So here we're going to see the notation for an electron on the left side of the arrow. An example of this is when we have argon 37. Okay, and it has electron capture. So on the right side of the equation, what happens here is our mass stays the same, but our atomic number is going to decrease by 1 to give us 17. And the element which has an atomic number of 17 is chlorine. This diagram shows some important atomic symbols that you should be familiar with. So a proton, which we've abbreviated with a P with a plus sign up till now, when we are doing these nuclear decay equations, can be symbolized as a hydrogen atom or a proton this way. A neutron, which has no charge, will be symbolized this way. An electron in such a way. So we're doing the atomic notation where we have the mass at the top and the charge or the atomic number at the bottom. Alpha decay, this is the Greek letter alpha, but when we're balancing equations, we want to use the fact that it's a helium atom because it has a mass of 4, a charge of 2, and that's what helium has. Beta, okay, and again, here's that beta minus is where we have an electron, okay? So 0 mass, -1 charge gives us an electron. The positron, which is beta with a plus sign, looks just like the electron, except that instead of having a -1 charge, it has a +1 charge. The final type of radiation is gamma rays, and it's associated with radioactive decay. It's a high-frequency electromagnetic radiation which travels at the speed of light, and it's symbolized by the Greek letter gamma. Okay, which looks like this. So when we talked about the electromagnetic spectrum, when we talked about electrons, you can see here that the gamma rays are beside the X-rays and the ultraviolet, end of the spectrum. Okay, these are very strong waves, and they can only be shielded by lead that is 1.5 feet thick, or by concrete that is 6.5 feet thick. Nuclear fallout shelters were meant to protect people from the threat of gamma radiation after a nuclear explosion, and frequently gamma rays accompany both alpha and beta decay. So here are 3 sample nuclear decay equations. What I would like for you to do at the end of your notes is please write down these equations, and then I finish filling them out, so solve for the blanks, and then tell me what type of decay this is. Is it positron, alpha decay, beta decay, etc.?